Our next and final speaker is Jake Taylor. Jake worked with Alex from about 1997 on for a few years, and then he went on to do his PhD at Harvard. So, give you a 5-minute warning.
Yeah, that'd be great. So it's a real pleasure to be here and to see just a few members of the crowd of people that Alex has influenced in a long and illustrious career. I have the benefit of going in front of two other people who realized one of Alex's great geniuses, which is the ability to identify problems that those who come to him can solve. I'm going to talk today about some work I've been doing at MIT. I'm a postdoc there right now. But before I get into sort of my current research, I'd like to take a brief trip down memory lane and recall a day in 1997 where a long-haired freshman with a beard walked into Jim Babb's office and said, "I want to do something quantum." Well, let's say that there were a few steps after that particular moment, and eventually Alex got involved and put me on a project associated with the dipole polarizability of the hydrogen molecular ion, H2+, which you heard quite a bit about this morning from Gordon Drake's talk. And we managed to get some actual success in the course of a few years of work in calculating some new values there. And that was really exciting as an undergraduate, and I kind of never lost my quantum mechanics fever, let's say. Since then, I've been focusing a little bit more on teasing out quantum mechanical behavior in larger and larger systems. And for those of you who are pretty familiar with this general idea, this is more diagrammatically called the field of quantum information, and I'm focusing on sort of real-world devices, that is, approaches to implementing these ideas from quantum information theory. And this is an intriguing field to me because it combines a detailed knowledge of atomic, molecular, and solid-state physics with this sort of high-level picture of our great heroes from the era even preceding Alex, where we had to think about the underlying fundamentals of quantum mechanics. There's a variety of systems that I work with these days, and they all have some nice analogs to atomic systems. I'm going to focus today on two things I've been focused on recently. One is the so-called nitrogen vacancy center in diamond, which I'll explain in a moment. And the other you heard about already, which is cold atoms trapped in optical lattices. So the idea behind this, my general research program, is actually the following, that in this field of quantum information, while we like to focus on the long-term goal of actually doing information processing with quantum devices, there's a lot of short-term things you can do along the way that are very intriguing. And one of these is precision measurement, and another perhaps is investigating the properties of long-distance entanglement, and also the properties of macroscopic quantum states. You know, the prototypical example, of course, being Schrödinger's cat, being in a superposition of alive and dead. But we'd like to understand better all of these things. I'm going to focus, however, now on the measurement side, and we have to delve into the world of spins, of single spins. And it turns out that single spins are pretty hard to detect, if you didn't know already. In principle, in quantum information, we need to be able to actually measure and manipulate individual electron spins or nuclear spins. And in practice, it's quite hard. The current state-of-the-art technology is the so-called magnetic resonance force microscope. And with this device, one can, at very low temperatures, so it's sort of in the millikelvin regime, in the course of about 1,000 seconds, detect whether a single electron spin is up or down. In comparison, for sort of a quantum information perspective or a quantum effects perspective, the coherence time of this electron spin is only on the order of sort of 1 to maybe 1,000 microseconds. And so one can detect single spins these days. It's very hard to do, but we're nowhere near the point where detection allows one to do anything quantum mechanically coherent on the same time scale anyway. I should also mention that if you wanted to do something interesting with single protons, you're pretty much out of luck with this type of technology because the averaging goes to the order of a few times 10 to the 7 seconds, which is on the order of a year or so. And that's not so great if you wanted to understand better molecular structure and things like this. So I should mention, though, that if you can do single spin detection, there's a big benefit. One is that you can actually try and measure, for example, the structure of individual molecules. So rather than having to do an assay where you create many copies of the same molecule and understand its statistical properties, you can instead actually create single versions and investigate that single version in some detail. You can also understand several nanometer scale processes in material science that you couldn't perhaps have perceived before. And you could even use this in some type of nuclear magnetic resonance technology to build some type of scalable quantum computing device. So there's a lot of promises that we're making here. But I'd like to focus on the solution to this first problem, just the measuring of a single spin. And the system that I have in mind for this is the Nitrogen Vacancy Center in Diamond. If you went to the poster session yesterday, you actually have heard a little bit about this already. Paola Capellaro had a poster on this particular topic. This is a picture, diagrammatic picture of the lattice of carbon that forms diamond. And two of the carbons are missing here. One has been replaced by nitrogen. The other is absent, and this is called a vacancy. This thing is the Nitrogen Vacancy Center, or NV Center. When I say NV, I mean nitrogen vacancy. And it has an interesting electronic structure. There are two basically free electrons here. It's a small molecule. Those two electrons form a spin triplet ground state. And because of the crystalline field, the spin triplet is not isotropic, but actually has a crystal field splitting so that the ms equals 0 sublevel of the triplet is lower in energy than the ms equals +1 and -1 levels. And that splitting is on the order of a few gigahertz, so you can actually work with the system with a reasonable microwave technology. But the most important part here is that there's a nice optical structure. So these are the different electronic levels. This is the ground electronic state, excited electronic state with a singlet, excited triplet state. If you apply red light to the system, something interesting starts to happen. And in particular, say I've produced some interesting superposition of these different microwave sublevels with a microwave field. Then I apply a green light to the system. What happens, the green light pumps this far above resonance into a highly excited vibrational state. It relaxes via phonons into the crystal. And then a red photon is emitted, and it goes back down to the 0 state. And so I get photons out, red photons, when I pump with green light. And that fluorescence is a nice signal already to show me I've got a single emitter. But the really interesting part is if I do the exact same thing for the ms equals +-1 levels, the selection rules are slightly different. I go up, I non-radiatively go down to here, but now there's a cross-section to go across to the singlet state. It's a much higher cross-section for the ms equals +-1 levels than it was for the ms equals 0 level. And that means that I stop getting fluorescence for a little while I wait for the singlet to relax. Eventually it relaxes and emits a photon. But meanwhile, the 0 state, if I was in that state, has been fluorescing the whole time. And so what I get is I get a transient signal. That is, for a short period of time, I have more light coming out if I have a 0 state than if I have a 1. And by looking for that transient, one can actually determine the spin state of a single NV center. This also eventually leads to optical pumping because the singlet relaxes back down to the ms equals 0 state. It's the only sort of spin 0 configuration that you had. So now I'm actually going to move at a relatively fast pace. And I apologize in advance. I just wanted to give you the gist of what these ideas mean. And I'd be happy to discuss afterwards some details or in questions. What I'm going to tell you about now is how you can use these microwave sublevels of this optical detection to measure not this spin, which is being manipulated by light, being manipulated by microwaves. It might be a dirty system. We don't know. But instead, to use it to measure some other spin nearby. And to do that, we're going to look into magnetic field detection with a single spin. The characteristic technique we use is Ramsey interferometry, where you produce initially some polarized spin, say, pointing down. And this is done via optical pumping. Then you apply a pi/2 pulse to the spin, which rotates it up to something which is a coherent state between up and down. This is along the x-axis of this block sphere here. And that state will start to precess in any external magnetic field. After some time, it's precessed a small amount. I then make a rotation about the perpendicular axis on the plane. So that takes a small displacement away from, say, the y-axis here to a small displacement away on the z-axis. If I then measure up versus down, I can make an estimate of the probability that my spin ended slightly upward or slightly downward. And thus, a small change in magnetic field leads to a linear change in the probability of being up versus down, and thus a linear change in the transient fluorescence signal. Now, if, for example, I have some unknown magnetic fields around, this is a problem. In fact, this is exactly what we think of as dephasing in these types of systems. And this is what you work very hard against in quantum information, because any dephasing limits what quantum control techniques you can do and what type of quantum gates you could achieve. However, this is not necessarily noise, because it could be that the thing that's causing the rotation is, in fact, the field you'd like to measure. And so in that context, this is actually making a very good detector. We're taking dramatic advantage of the high sensitivity of quantum mechanical systems to small perturbation, to use it to detect a particular small perturbation that we'd like to know more about. Now, I wouldn't be a very good scientist if I told you we had a detector and then I neglected noise. So let's talk a little bit about the signal to noise of this type of device. We have a single spin. So in a single run, we can wait for a period of time. We can develop a bit of rotation, limited only by the coherence time of the spin. And so we have a signal which is proportional to the magnetic field times the time I spent processing. And I have a noise which is just sort of order unity, because I have a digital thing. It either comes out, I get a 1 or a 0 each time. So if I have a total time, capital T, I get to make sort of n measurements, where n is the ratio of the total time versus the interrogation time for a single sort of run of the experiment. And that would suggest that I get a noise, sort of standard Poisson noise, of the order of square root of these number of runs. And so my signal to noise equation is going to be proportional, of course, to the external field applied to the system, and then the square root of my coherence time times the total interrogation time. Now, in precision measurement, what you do is you renormalize out the total interrogation time, because that's something that if you didn't get as good as you'd like, you just keep integrating. And if you integrate 4 times longer, you get twice as good a signal. That's the basic idea. So instead, we talk about the sensitivity, which is this signal to noise ratio divided by the overall interrogation time t. Now, for this nitrogen vacancy center, or for, more generally speaking, single electron spins with few microsecond coherence times, this sensitivity comes out to be on the order of a few nanotesla per root hertz. To give you a sense of what a nanotesla is, after all, some of us are atomic physicists, we think in Gauss. You should recall, of course, the Earth's magnetic field is about 0.1 millitesla. If I think about the dipole field from electron spin at the distance of about 10 nanometers, that's about 2 microtesla. So already we're talking about something which could detect electron spins on sub-millisecond timescales. If I think about a proton spin, it's actually about 3 nanotesla. And so that means, in principle, a device of this form could even detect single protons on the order of a second timescale. Now, there's a few more details. In fact, there's a lot of noise in the system. It is sitting in a crystal. There's a local environment. This is all done at room temperature. So there's a lot of potential problems. It turns out you can get rid of most of them by using some advanced pulsing techniques like spin echo and the like. I'm not going to go into the details, but suffice to say that one can, in principle, achieve a sensitivity that's down at this nanotesla per root hertz with a wide bandwidth in the order of from kilohertz to megahertz in this type of system. That's quite nice. This is all very nice and theoretical. But actually, recently in Misha Lukin's, I should mention, by the way, sorry, that the comparative techniques for this sort of high resolution, high sensitivity detectors are this MFRM, which I told you about before. It has nanometer resolution, and it has a sensitivity that's in the order of 10 to the minus 5 Tesla per root hertz. And the other is the so-called microsquid magnetometers, which have a few hundred nanometer resolution and about 10 times better sensitivity than the MFRM. This is now 2 or 3 orders of magnitude better than the best that exists. I should mention that the very first experiments along these lines have now been done in Misha Lukin's group, with some of my collaborators, and also now being done in Ron Walsworth's group at the Center for Astrophysics. And this is the graph I'd like to point your attention to. We're looking at basically this section here, but not log-log anymore. And you see that the theoretical prediction of sensitivity, including the collection efficiencies that they're getting in the experiments, and what they actually achieve, which are plotted here in dots with the error bars, are pretty well in agreement with each other. And even with the very first experiment, and where nothing has been optimized, we're already achieving 30 nanotesla per root hertz. And so we have a lot of hope this is going to be a next generation, very interesting magnetometer for doing high resolution work. So what's the outlook here? Well, we'd like to get down to this sort of single spin detection. What I showed you experimentally was just the detection of an external field driven by a coil. Easy to create, easy to calibrate. What we'd really like to measure is a single electron spin, for example, in a molecule. So let's take some surface with some electron spins, paramagnetic impurities or the like, distributed about. Each of them has a little dipolar field that's decaying as 1 over r cubed. And now I'm going to bring near that thing a tapered fiber with a nanocrystal of diamond attached to the tip. This nanocrystal is on the order of 25 to 50 nanometers in size. They can have NV centers within them. The optical properties remain the same as what I told you about before. In fact, they work quite nicely. And what you do is you apply your fluorescence light from your driving light from the side, and you pick up fluorescence in the tapered fiber tip. You can improve collection efficiency by a variety of clever cavity techniques. But this tip here has a local sensing volume because the dipolar fields are decaying as 1 over r cubed. And what you do is you scan the tip around and as a function of time, you pick up different signals on this thing because each of these spins is contributing more or less as it gets further or closer to the device. You can improve the resolution, of course, by applying a gradient to the system, which slices up the precession frequencies of each of these objects. You have some frequency-dependent measurement, and so you can actually think about getting sort of a few nanometer type resolution with this nanotesla per root hertz sensitivity. And this is an unprecedented regime. In fact, this suggests that one could really get to the single proton detection with this sort of 1 second time scale. This sort of quantum device is not very quantum. There's only a single electron spin, or actually 2 electron spins involved. The photons, they don't have to be particularly interesting photons. I just need to get fluorescence out of the system. But now I'd like to say that actually the same system, which could be used for magnetometry, could also perform a building block, or be a building block for quantum communication. And now I need to look at the quantum mechanical properties of the fluorescence and the quantum mechanical properties of multiple NV centers working together. The underlying idea here is to use this spin-dependent fluorescence, the fact that I get light from the 0 transition and not from the 1 transition, to actually produce entanglement between different nitrogen vacancy centers at long distances. So the prototype here is a 2-level system, 0 and 1. There's an excited state here. I'll just draw these types of systems with a little red dot. Now we're getting very diagrammatic. When you apply light, you excite the 0 state to an excited state. Here we're doing an on resonance. And then it fluoresces. It drops a photon out. If I have an emitter here and an emitter there and a beam splitter in between with 2 photodetectors, this sort of classic quantum communication approach, this emitter will emit a photon, and it gets split in the beam splitter. Or alternatively, the other emitter might emit a photon and get split in the beam splitter. And what the beam splitter is doing is it's removing the which way information. And so if you start, for example, with an initial state where you have a low probability, little p, or a square root of this thing, of being in the 0 state, and a high probability of being in this 1 state, which is dark with respect to the laser light, conditional upon a click having occurred, most of the time you only had a single photon going through the system when a click occurs, and that single photon, you don't know whether it came from the left side or from the right side. And if you set up your interferometer sufficiently well so you could see, for example, a Hongo-Mundell dip or something like this, then you should be able to remove entirely the which path information from this experiment. And with success probability of order p, you get exactly one of these bell-type states, 0, 1 plus 1, 0, which is a well-entangled state and a sufficient building block for doing interesting quantum communication and computation tasks. There's a few caveats here. One thing is that I really need to work with some weak excitations. I don't want 2 photons going through the system. The single click event has to make certain to not have any which path information, so I need to be very stable with respect to phases. That's quite tricky. And I also need a good quantum memory, because most of the time when I do this thing, it doesn't make any clicks, because this p is quite small. And that means I have to add the system some memory. In the nitrogen vacancy center case, we have nearby carbon-13 spins associated with the 1.1% natural abundance carbon-13, and those could provide, for example, the memory. You can go on to think about sort of making a register, a little device, which you insert into whatever apparatus you'd like for doing quantum communication or quantum computation. And it consists of one of these spins with the memory nearby, coupled to a cavity. And then you can use a large array of these things, for example, and have some type of large-scale beam splitter device to connect different things to other things. This is just a sort of heuristic picture of how you could go from success with just a few spins to success with many spins. In the final few minutes, I'd like to actually shift gears a little bit and talk about a slightly different topic, but one also of dramatic interest. And this now finally touches back to this three-body physics that we talked about right at the beginning, the H2 plus thing. So I'm back now a little bit towards atoms, and we're looking at here cold atoms in a lattice. They have a lot of potential as devices or objects for simulating condensed matter systems, along with, of course, improving our own understanding of the low-energy physics of atoms. And one of the great challenges that we have going forward is trying to understand highly correlated systems, which in condensed matter include, for example, high DC superconductivity and these fractional quantum Hall states. And one of the things that we'd like to be able to add to our simulator is a strong three-body or four-body interaction. Now, in these cold atom systems, of course, you're very cold, so you're in the S-wave scattering regime. In fact, the scattering length approximation is probably very, very good. And so you don't really have any three-body or four-body elastic scattering mechanism that makes any sense. And our idea here is to use our favorite three-body interaction, which is not really elastic, but just your good old three-body recombination. It has some advantages because the three-body recombination for ultra-cold atoms doesn't actually depend so much on the low-energy theory, the scattering length approximation, because it has to deal with these deeply bound states of the system. And so we can actually disconnect some of the physics associated with the elastic properties at low temperature and this three-body recombination properties. On the other hand, this is a loss process, and what we'd like is coherent dynamics. So we can use this loss process to induce unitary dynamics by something along the lines of the quantum Zeno effect or line broadening effects. Here is a sort of characteristic double well system. I've got two atoms on the left, one atom on the right, for example. The atoms can tunnel across, and there's an interaction on site of this U2 that you heard about in the prior talk. I can diagonalize this system. I have either two atoms on one side, one on the other, or 3 and 0, and it just is hopping back and forth. But now I add this three-body loss process. When I've got 3 on a single site, the density is very high. Three-body loss should take over sufficiently tightly bound systems. And then I lose this thing because I have a very deeply bound molecule, has a lot of kinetic energy, gets kicked out of the trap. That loss process leads to a large broadening of this upper state here. And that large broadening, in turn, prevents the tunneling from occurring in the first place. You can just think of this. I have a narrow line with excitation and a broad line I'm trying to excite. The broader the line becomes, the lesser the probability I get excited at the line. And in fact, as the loss rate increases, the effective loss from this initial state goes to 0. So you can actually stabilize the system against three-body loss by having sufficiently strong three-body loss in the problem. And this now allows one to look at the regime of atoms sitting in an optical lattice with attractive interactions. Normally that's unstable because they start to all hop together and then they get lost. But now you can actually start to get some type of pairing mechanism where two atoms can come together but 3 cannot. And they can hop together, forming some type of paired superfluid. It's like a color superfluid. And you could even think about pushing forward for a sort of generalized theoretical concept called a 3 hardcore boson, which allows you to get to some of these interesting topological states. I won't go into more details about that. Instead, I'll just conclude here saying that I've been talking about some new approaches to using noise and loss as resources in quantum systems. We have some nice results now with these single spin-based magnetometers. I also suggested you could realize some novel quantum phases using dissipation, and I think the future work here is, at least on the magnetometer side, is these bulk detectors. So I'd like to also thank my collaborators at Harvard and MIT and Innsbruck as well, and which I've been doing this work with, and the Pappalardo Fellowship at MIT that supports me. Thank you very much for your time.
Okay, thanks, Jake. Any questions? Yeah, Hossein.
This is probably trivial, but I did not quite understand your comment about three-body recombination not having to do anything with the scattering length.
Oh, it's not that it has nothing to do with the scattering length, but rather it has a lot to do with the short length scale part of the molecular potential. In a way...
But initially, the process actually is very long-ranged. Right?
Yes. If you think so there's two regimes of three-body. One is the Efimov regime, and where the scattering length is long.
Right. I mean, the three-body recombination rate scales as scattering lengths to the fourth.
Not for short scattering lengths. For sufficiently short scattering lengths, it remains, even as scattering length goes to zero, for example, in your Feshbach resonance.
Yeah.
Right, scattering length has gone to zero, but three-body loss remains.
Right.
Right.
Okay. And if you tune it to zero, you mean?
If you tune it to zero. I'm not talking about the background scattering length, but the scattering length inclusive of the low energy part, right, the very highest part of the molecular states.
Okay.
But the full molecular component, right, knows more than just that highest state. And that means you get a quite different behavior for three-body than for two-body.
Okay.
We'll get you guys together for coffee. All right. Are there any other questions for Jake? All right, let's thank him again and all the other speakers for this session.